Assalamualaikum and good day to everyone. This is chapter 9, Alternating Current Circuits and Electromagnetic Waves. An AC circuit consists of combinations of circuit elements and an AC generator or an AC source which provides the alternating current. The output of an AC generator is sinusoidal and varies with time according to the equation here, where delta V is the instantaneous voltage, delta V max is the maximum voltage of the AC generator, and F is the frequency at which the voltage changes, measured in Hertz. Let us consider a simple circuit consisting of a resistor and an AC source as shown here in the figure. Take a look at the current versus time and voltage versus time curves for the circuit in the previous slide. At point A on the curve, the current has a maximum value in one direction. Between points A and B, the current is decreasing in magnitude but is still in the positive direction. At point B, the current is momentarily zero. It then begins to increase in the opposite negative direction between point B and C. At point C, the current has reached its maximum value in the negative direction. Notice that the current and voltage are in step with each other. Because the current and the voltage reach their maximum values at the same time, they are said to be in phase. Also, you can see that the average value of the current over one cycle is zero, because the current is maintained in one direction, which is the positive direction, for the same amount of time and at the same magnitude as it is in the opposite direction, which is negative direction. Remember that the rate at which electrical energy is dissipated in a resistor is the power, where I is the instantaneous current in the resistor. The important quantity in an AC circuit is a special kind of average value of current, called the RMS current, which is the direct current that dissipates the same amount of energy in a resistor as the actual alternating current. The top graph shows the alternating current. If we found the average of this current, it would not be very useful because the average is zero. On the other hand, the RMS current is always positive. To find the RMS current, we first square the current, then find its average value, and finally take the square root of this average value. That means the RMS current in the square root of the average of the square of the current. Because I squared varies sinusoidally, the average value of I squared is half I max squared over 2. This is the relationship between I RMS and I max. This is the average power dissipated in a resistor that carries alternating current. We can talk about alternating voltages in the same way in terms of RMS voltages with the relationship here. Delta V RMS is the RMS voltage and delta V max is the maximum value of the alternating voltage. When people talk about measuring an AC voltage of 120 volt from an electric outlet, they actually mean an RMS voltage of 120 volt. A quick calculation using the last equation shows that such an AC voltage actually has a peak value of about 170 volt. Now let us consider the series circuit shown in the figure. Consists of a resistor connected to an AC generator. A resistor impedes the current in an AC circuit, just like it does in a DC circuit. And we have the relationship here. The RMS voltage across a resistor is equal to the RMS current in the circuit times the resistance. The equation is also true if maximum values of current and voltage are used. Now let us consider the simple series circuit in the figure on the left. Consists of a capacitor connected to an AC generator. You can sketch curves of current versus time and voltage versus time, shown in figure on the right. First, notice that the segment of the current curve from A to B indicates that the current starts out at a rather large value. This is because there is no charge on the capacitor at t equals to 0. That means Nothing in the circuit retards the flow of charges except the resistance in the wires. But the current decreases as the voltage across the capacitor increases from C to D on the voltage curve. When the voltage is at point D, the current reverses and begins to increase in the opposite direction, which is from B to E on the current curve. During this time, the voltage across the capacitor decreases from D to F because the plates are now losing the charge they accumulated earlier. The current reaches a maximum value in the opposite direction at point E on the current curve, and then decreases as the voltage across the capacitor builds up. As you can see in the graph, an alternating voltage is applied across a capacitor and the voltage reaches its maximum value 1/4 of a cycle after the current reaches its maximum value. We say that the voltage across a capacitor always lags the current by 90 degrees. The impeding effect of a capacitor of the current in an AC circuit is expressed in terms of a factor called the capacitive reactance. When C is in farads and F in hertz, the unit of capacitive reactance is ohm. From this equation, we can see that as the frequency F of the voltage source increases, the capacitive reactance decreases, so the current increases. Now, let us consider an AC circuit consisting only of an inductor connected to the terminals of an AC source. The changing current output of the generator produces a back EMF that impedes the current in the circuit. The effective resistance of the coil in an AC circuit is measured by a quantity called the inductive reactance. When F is in hertz and L is in henries, the unit of inductive reactance is the ohm. The inductive reactance increases with increasing frequency and increasing inductance. The graph here shows the instantaneous voltage and instantaneous current across the coil as functions of time. When a sinusoidal voltage is applied across an inductor, the voltage reaches its maximum value 1/4 of an oscillation period before the current reaches its maximum value. In this situation, we say that the voltage across an inductor always leads the current by 90 degrees. Take a look at point A on the current curve. Here, the current is beginning to increase in the positive direction. At this instant, the rate of change of current, the slope of the current curve, is at maximum. As the current rises between point A and B on the curve, the rate of change of current gradually decreases until it reaches 0 at point B. That means the voltage across the inductor is decreasing during this same time interval, as you can see by the segment between C and D on the voltage curve. Immediately after point B, the current begins to decrease, although notice that it still has the same direction it had during the previous quarter cycle. As the current decreases to 0, which is from B to E on the curve, a voltage is again induced in the coil, which is from D to F. But the polarity of this voltage is opposite the polarity of the voltage induced between C and D. This occurs because the back EMF always opposes the change in the current. Now we are ready to consider what happens when a resistor, capacitor and inductor are combined in an AC circuit. Since this is a series circuit, current is the same at all points in the circuit at any instant and varies sinusoidally with time. Now you know that the voltage across each element might or might not be in phase with the current. This graph will show us the voltage-current relationship for each element. Figure B shows that the instantaneous voltage across the resistor is in phase with the instantaneous current. Figure C shows that the instantaneous voltage across the inductor leads the current by 90 degrees. Figure D shows that the instantaneous voltage across the capacitor lags the current by 90 degrees. The net instantaneous voltage supplied by the AC source equals the sum of the instantaneous voltages across the separate elements. This does not mean that the voltages measured with an AC voltmeter across R, C and L sum to the measured source voltage. In fact, the measured voltages do not sum to the measured source voltage because the voltages across R, C and L all have different phases. We can use a technique involving vectors to account for the different phases of the voltage drops. We can represent the voltage across each element with a rotating vector. The rotating vectors are referred to as phases, and the diagram is called a phasor diagram. This particular diagram represents the circuit's voltage given by the expression shown, where delta V max is the maximum voltage, which is the magnitude or length of the rotating vector or phasor, and phi is the angle between the phasor and the positive x-axis when t equals to 0. Phasor diagrams are useful for analyzing the series RLC circuits. Voltages in phase with the current are represented by vectors along the positive x-axis, and voltages out of phase with the current are phasors in other directions. In the figure on the left, delta VR is horizontal and to the right because it is in phase with the current, and delta VL is represented by a phasor along the positive y-axis because it leads the current by 90 degrees. Delta VC is along the negative y-axis because it lags the current by 90 degrees. Now let us add the phasors as vectors, as shown in the right hand figure. From this we get the equations. In these equations, all voltages are maximum values. The equations are also valid for RMS voltages. This figure reminds you that the voltage across the resistor, capacitor and inductor are not in phase, so you cannot simply add them to get the voltage across the combination of elements or to get the source voltage. Here are the voltages in terms of Ohm's law. We can define the impedance as shown and rewrite our voltage equation in the form of Ohm's law. The impedance and the current in an AC circuit depend on the resistance, the inductance, the capacitance and the frequency. We can represent the impedance with a vector diagram such as the one shown here. The right side of the triangle is XL minus XC. Its base is R and its hypotenuse is Z. If we apply Pythagorean theorem to this triangle, we get our definition of impedance. Also, we can calculate the phase angle. Let us take a look at the power dissipated in an AC circuit that contains only a generator and a capacitor. When the current increases in one direction in an AC circuit, charge accumulates on the capacitor and a voltage drop appears across it. When the voltage reaches its maximum value, the energy stored in the capacitor is given in the equation shown. This energy stored is only momentary. When the current reverses direction, the charge leaves the capacitor plates and returns to the voltage source. During one half of each cycle, the capacitor is being charged, and during the other half, the charge is returned to the voltage source. So the average power supplied by the source is 0. In other words, no power losses occur in the capacitor in an AC circuit. In a similar way, the source must do work against the back EMF of an inductor that is carrying a current. When the current reaches its maximum value, the energy stored in the inductor is maximum and given by the equation. When the current begins to decrease in the circuit, this stored energy is returned to the source as the inductor attempts to maintain the current in the circuit. This is the average power delivered to a resistor in an RLC circuit. The average power delivered to the generator is converted to internal energy in the resistor. No power loss occurs in an ideal capacitor or inductor. Let us substitute R from Ohm's law into the power equation. Now we have an alternate equation for the average power loss in an AC circuit. We can use the voltage triangle here, where we see that the voltage drop across a resistor can be written in terms of the voltage of the source. That means the average power delivered by a generator in an AC circuit. That means this is average power delivered by a generator in an AC circuit, where cos phi is called the power factor. The equation shows that the power delivered by an AC source to any circuit depends on the phase difference between the source voltage and the resulting current. In general, the RMS current in a series RLC circuit can be written as shown. From this equation, we see that if the frequency is varied, the current has its maximum value when the impedance has its minimum value, which occurs when XL equals to XC. In this situation, the impedance of the circuit reduces to Z equals to R. The frequency at which this happens is called the resonance frequency. This figure is a plot of current as a function of frequency for a circuit which has a fixed value for both the capacitance and the inductance. From our RMS equation, we have to conclude that the current would become infinite at resonance when R equals to 0. Real circuits always have some resistance, which limits the value of the current. The tuning circuit of a radio is an important application of a series resonance circuit. The tuning circuit of a radio is an important application of a series resonance circuit. The radio is tuned to a particular station by varying a capacitor, which changes the resonance frequency of the tuning circuit. When this resonance frequency matches that the incoming radio wave, the current in the tuning circuit increases. That's all for chapter 9. Thank you.